With these next two examples, we're going to do everything with each of these functions. Everything we learned how to do in section 1, 2, and 3, we're going to do it all to find out every little bit of information we can about the graph and then try to sketch it. So I encourage you to pause the video here or look at your own OneNote or whatever and read through this square here of all of these different things that we are going to try to find about any particular function. And then we'll go through all of these steps in example 9 and example 10. Now here's example 9. It's a typical rational function. What I'm going to do is pause the recording and I'm going to find the intercepts and the asymptotes just without you having to watch me go through all of that. So I encourage you to do the same thing. Pause the recording, find the x and y intercept and any vertical and horizontal and slant, if possible, asymptotes for this function, and then we'll move on to some of the more complicated calculus-y stuff. All right, so steps 1 and 2, intercepts, asymptotes. This is what I have found, and I kind of highlighted the important conclusions, like the basic facts that I'm going to need to know when I go to try to sketch a graph of this at the end. I've highlighted so that I can go back and find them afterward. All right, the next step here is to find the derivatives and consider the domain. And then once I have the derivatives, I'm going to find the critical values, and I'm going to do like first derivative test, second derivative test, concavity, all of that stuff from sections 1 and 2. All right, so here we go with that. We've got f of x is this rational function. To find f prime of x, I think I'm going to, you kind of have some choices here. You could use the quotient rule, or you could think of it like this and just use the chain rule with a -1 exponent there. I think I'm going to use the quotient rule, and again I'm going to pause the recording so you don't have to watch all of that, but I encourage you to pause it, try the derivative on your own, and then resume the video to see how I got it. So there's my first derivative, and first derivatives give you critical values. So the next thing we're going to do with the first derivative is find critical points. We'll say critical points, critical values kind of mean the same thing. Critical values, we need to see what makes the numerator equal to 0 and also what makes the denominator equal to 0, because those are the things that would make the first derivative 0 or make the first derivative undefined, and that's how we get our critical values. All right, so the first one, x equals 0. The next one is kind of boils down to x squared minus 4 equals 0, so x squared equals 4, and we get plus or minus 2. But here's where it's important to also consider the domain, because 2 and -2 are vertical asymptotes. They're not in the domain of this function. So we're not actually going to call them critical values because they're not in the domain. It doesn't mean they're not important. It just means they're vertical asymptotes. They're not going to be places where you have a max or a min, essentially. You're going to have the limit goes to infinity or negative infinity at those places. And it's important to distinguish those. All right, so here's my only critical value. And then I'm going to use the second derivative test to figure out if x equals 0 is a max or a min. And so I'm going to take u and v and do the quotient rule again to find the second derivative. All right, so again, I'm going to pause the video while I do that. Now here's my second derivative, and it's going to become kind of important here to factor this and reduce it as much as you can, because it's really pretty messy in the beginning. But if you recognize, let's see, I'm right here in this step. If you recognize that we've got two terms here separated by this plus sign, which used to be a minus sign, but there was minus and negative. So separated there, each of those terms has an x squared minus 4 parentheses in them. And so I can cancel one of those out from each term along with one from the bottom, and that simplifies this a whole lot. And so it all boils down to this in the end. And now I can use that second derivative to figure out if my critical point x equals 0 was a max or a min. So I'm going to do the second derivative test. We've got f double prime of 0 would give us 64 plus 48 times 0 on the top, and it would give us 0 minus 4 cubed on the bottom. So that's going to be a positive number on the top, but a negative number on the bottom. So overall, it's going to be negative. And so that's how I know that this is a max at x equals 0. More specifically, a max at 0, comma, and I already know the y value that goes along with this because I already found it with the y-intercept. So 0, negative 2 is where I've got my max. So that's the next important bit that I want to highlight here for when I'm going to draw my graph. The next thing we want to do is think about concavity. So let's go back up and check here. Intercepts, asymptotes, derivatives and domain, critical values, increasing and decreasing relative extrema. We've done that. We found the relative extrema. Let's think, I guess, before we go to concavity, let's think about increasing and decreasing. Even though we kind of opted out of the first derivative test and used the second derivative test instead, we could say this is increasing and decreasing on either side of that critical point 0. And then remember how we had a negative 2 and a 2 vertical asymptotes? That's not going to change anything. It's still going to be decreasing on this side of the negative 2. It's still going, still increasing. It's still going to be decreasing on this side of the 2. And so that kind of helps me figure out what's happening with my vertical asymptotes. So at this vertical asymptote, the limit as x approaches negative 2 from the left is infinity because this is increasing here. And as x approaches negative 2 from the right, it's going to negative infinity. And that's because this is decreasing in that direction. So increasing in this direction, decreasing in that direction. So this is probably a vertical asymptote where we've got something like this and something like this on either side of it. And then the same thing happening over here at 2. So at 2, I think we've got a vertical asymptote where we've got something like this and then something like this, based on what we know about increasing and decreasing. And then at 0, we've got a max. So that's kind of helping to piece together our graph a little bit so far. So we have covered critical points, extrema, increasing, decreasing. Now I think it's time to talk about concavity. Yes, F, inflection points, G, concavity. Those things kind of happen all at the same time. Now, in order to look for inflection points, we have to figure out what makes the second derivative 0 and what makes the second derivative undefined. And so we're looking here at our second derivative. We're going to say, what makes the numerator 0? And what makes the denominator equal to 0? Now this one, I feel like we've seen it before, right? It's the plus or minus 2. For the other one, it ends up being negative 4. Nope, it ends up, let's just solve it. It ends up being no solution, but let's see how that happens. Negative 64. So x squared is going to be some negative number, and that reduces to 4/3. So this actually has no solution because you can't have an x squared equal to a negative number. And so we really just have these two points, plus or minus 2, as potential inflection points. And we know that those are not in the domain. However, they can still be places where the concavity changes. So we still want to kind of analyze what's happening on either side of them. Just like over here, we wanted to analyze what's happening on either side of them just so we can draw the graph properly. All right, so let's draw a second derivative sine chart. That was an x, and this will be second derivative sines. We're looking back at our second derivative right here. And we're saying, what happens if we plug in, let's start in the middle. If we plug in 0, we get a positive number on the top, we get a negative number on the bottom, overall negative. If we plug in something really big, like 1,000,000, positive number on the top, positive number cubed on the bottom. And then the same thing if we plug in negative 1,000,000, because the first thing you're going to do is square it, and that'll turn it positive. So here's our second derivative sine chart. This tells us that we've got concave up, concave down, concave up. But remember, these were vertical asymptotes. So while it's tempting to say, like, well, that must mean our function looks like this, that's not the case. Our function looks more like this, and then like this, and then like this, with these vertical asymptotes in the middle. All right, so I think that might be just about all we can do before we have to sketch the graph. We've got inflection points, we've got concavity, and so, yeah, let's sketch a graph. Now we know we've got vertical asymptotes at 2 and -2. We know we've got a max at 0, -2. So we'll say that's right here. And so that goes like that. We know we have the limits as x approaches -2 from the right and as x approaches 2 from the left are both going to negative infinity. So that's kind of what's happening in the middle here. So this is going to go down. Let me switch colors here. This is going to go down forever as you get close to that asymptote, and this is going to go down forever as you get close to that asymptote. And that sort of covers what we knew about concavity up here. It covers what we knew about the limits of the vertical asymptotes here. It covers our y-intercept from back here. Now we need to consider the fact that this x-axis is a horizontal asymptote. So we didn't really have to worry about it in the middle because it was starting negative and going down. But we do have to worry about it here on the ends because we have a situation where as you approach 2 from the right, we're going to be going up like this. And as we approach -2 from the left, we're going to be going up like this. But we also have to not cross the x-axis. We have to make sure we've got that horizontal asymptote happening at the x-axis and no x-intercepts. And so I think what that's going to look like is this. And then like, gosh, that was ugly. Like this. So we've got sort of 3 pieces happening here. So all of this information that we got from all of the asymptotes and intercepts and limits and derivatives and everything all comes together like a puzzle to give us this graph.